Hello everyone, welcome to my video on the fundamental theorem of calculus part 1. This is a big one. This is a very important topic because it introduces a relationship between calculus 1 and calculus 2, namely that the derivative of a function and the integral of a function are actually inverse operations of one another. So there's our relationship between cal 1 and cal 2. This is very nice, very big, important theorem. So let's go ahead and explore it. So first of all, the definition is if f is a continuous function on the closed interval ab, and the function g of x is defined as g of x is equal to the integral from a constant, a number, to x, a parameter, of f of t dt for x in the interval, the open interval ab, then g of x is continuous on this closed interval, differentiable on the open interval, and the derivative g prime of x is equal to the original function f of x. Namely, if you take the derivative of an integral, you're back with the original function. So this is very nice. I'm not going to prove it because the proof is long. If you guys want to see a proof, let me know in the comments and I'll create a video on just that and I'll explain step by step the details. So we're going to take this as is. We're going to look at a couple of examples. So in our first example over here, we're going to see how to apply FTC part 1. So it says to use FTC part 1, the fundamental theorem of calculus, part 1, to find the derivative of g of x, where g of x is given to be the integral from 1 to x of 1 over 1 plus t squared dt. So t, the variable t is just a dummy variable. It's just, you can use any variable you want here. This is really a function of x, okay? So the x that's in the bound is a giveaway. Why do we have an x in the bound? Usually when we're given the integral, these are values, these are numbers. We have 1 to 3 or something. So that's the giveaway. That's how you know it's a fundamental theorem of calculus part 1 problem, because we'll have a function in the bound. It doesn't necessarily have to be x, it could be any function, x squared, tan of x, secant of x, it could be really any function. Okay, so if you see a function in the bound, odds are that's a fundamental theorem, fundamental theorem of calculus part 1 question. So what we have to do is first analyze the integrand, see if that function is continuous. So if we consider the function f of t, which is this guy here, we have 1 over 1 plus t squared. Is this function here continuous? Well, yes, because no matter what you replace your t with, you'll never have a division by 0, because this value here is squared, and you're adding 1 to it. So this is always going to be a positive value. The smallest number you could have for t squared is just 0, and then you're adding 1 to it, so this is okay. This is continuous. So we have continuity, which is one of the requirements of FTC part 1. So the function is continuous, great. Now we know that to take the derivative, we know that the derivative and the integral are inverse operations of one another. So you could remove essentially the integral. So at this point here, once you've established that f of t, this function here, is continuous, we apply FTC part 1 by taking the derivative. And we know that the derivative of the integral, they cancel each other. And what you're essentially doing is you're substituting the upper bound into the function, giving us 1 over 1 plus x squared. So instead of having an x, instead of having a t, we're replacing it with x. This is a function of x, and that's the idea. This is our function. This is the derivative. The other thing that I didn't mention here, but we're also doing, is we're substituting this with x, but you're also multiplying by the derivative of the upper bound of the function that's given. Okay. So every time you have FTC part 1, the lower bound's a number, the upper bound is a function. You replace the function into f of t. So in this case, you're replacing x into the t, giving us 1 over 1 plus x squared, but then you have to multiply by the derivative of x. We're applying chain rule here. This is super important. In this example, it doesn't affect the final answer, but this is something that we are doing, okay? So keep this in mind. So really, it's 1 over 1 plus x squared, and the derivative of x, and we're deriving with respect to x, is 1, so times 1. So it doesn't affect your answer, so we don't even have to write it. But this is something we have to consider in case the function on top, the upper bound, is not x and it's something else. Okay, so keep that in mind. We have to multiply by the derivative of the function. So the derivative g prime of x in this example is simply 1 over 1 plus x squared. Okay, let's take a look at another example. So here in our second example, we have to use again FTC part 1 to find the derivative of g of x. So we're looking for g prime of x, and g of x in this case is equal to the integral of sine x to 1 of 1 plus t cubed, all that to the 5. So pause the video, try to attempt this on your own, see if you're able to solve. So the first thing to notice is the fact that the function sine in this case is on the bottom. It's our lower bound. We can't do that. In order to apply FTC part 1, the function here has to be in the upper bound. how do we fix this? How do we remedy this? Well, we saw in our properties functions in the previous video that we could alternate the bounds. We could flip them. But if we switch the bounds here, what happens? We have to multiply by a -1. Okay, so that's how we begin this. So before we take the derivative, we start off by putting a negative and switching the bounds. So the sign on the x goes on top, the 1 on the top comes on the bottom. And now we have our constant on the bottom and we have our function on top. This is great. Okay. Next, we have to ensure that the function that's here is continuous. Is this a continuous function? Is 1 plus t cubed all that to the power 5 continuous? Yes, because this is just a polynomial. You don't have to expand it. We know this is a polynomial of degree what? It's degree 15. And we know that polynomials are continuous functions. So we have continuity. So that's the first thing we need to check. So continuous. Yes, we have continuity. Next, what we have to do is take the derivative. Okay, so to find g prime of x now, we have our negative that's there, and we essentially just substitute the upper bound into our function f of t. So we remember that the integral and the derivative are inverse operations of one another. So when I take the derivative, it cancels out the integral sign, and it leaves me with 1 plus, but instead of t, we're writing the upper bound. Sine of x, this thing cubed, all that to the 5. Okay, and this here is the derivative. But if you stopped here, this is the answer you got. It's wrong. Why? Remember, we have to multiply by the derivative of the function. You have to apply a chain rule here because we're taking its derivative. So the integral was negated, but we still have to derive the sine. What's the derivative of sine x? What's the derivative of the numerator? We know the derivative of sine from Cal 1 is cos of x. And this is now the correct function. Okay, this is the correct derivative. So remember to apply chain rule. Okay, depending on the function that's on our upper bound. Okay, so now we have our derivative. Okay, let's take a look at a harder example. So in our third example over here, it says to use the FTC part 1 to find the derivative of g of x, where in this case here, g of x is given to be the integral from tan x to x squared. So we have functions in our bounds of integration of 1 over cube root of 2 plus t to the 4 dt. Okay, so pause the video, give this a shot, see if you're able to find the derivative of g of x. Okay, so the first thing you have to catch is the fact that here we don't have a constant on the bottom. We're supposed to have a constant on the bottom and the function on the top. This is one of the requirements for FTC part 1. How can we fix this? We have two functions. Well, the game plan is to apply property 6 from our previous video, our properties of definite integrals. We're going to split this up. So the property that we're using is the integral from a to b of some function plus the integral from b to c of some function. Let's call this f of x. This is equal to the integral from a to c of f of x dx. Okay, so if the upper bound here matches the lower bound here, then you could just take the function straight from the lower bound here to the upper bound here from a to c, right? Because these numbers match. So here we have tan x and x squared. So we have it in this form. We're going to split it up into two integrals, okay? And it's going to be split up at some value b. And we could choose any value we want. It doesn't matter. Just to make things easy, I'm just going to choose 0. So I'm going to split this up using this property here as the integral from tan x to 0 of 1 over cubed root of 2 plus t to the 4 dt plus the integral from, this has to match the lower bound, so 0 to x squared of the exact same thing, cubed root 2 plus t to the 4 dt. Okay, and now I'm going to deal with each term individually. So the right hand side, this is good because my constant's on the bottom, my function is on the top. This is what we want to see. Here we have an issue. The function now is on the bottom. How do we remedy this? Well, we saw this in the previous example. If the function's on the bottom, we use our property where the integral from a to b of f of x dx is equal to the negative integral from b to a. Again, these are from our properties in a different video that we saw. Okay, so if we switch the bounds of integration, we multiply by -1. So that's what we have to do here. So I'm going to do this on the same step. So this becomes negative, and my tan of x comes on top, and my 0 is on the bottom. Okay. So now to apply FTC power 1, we have to ensure that the function that's given in here, f of t, is continuous. Is this function continuous? Yes. Why? Because notice that inside the root, you can never divide by 0, right? And this is a cube root, so if you have a negative, it wouldn't affect us. So if it was a square root, we'd have to be careful with negatives. Either way, this is fine because we have t to the power of 4. That's going to turn whatever value of t we plug in positive because it's to the exponent 4. And whatever value you put here, let's say you take t to be 0, well, 0 to the 4 is 0, but then you're adding 2 to it, causing it to still be positive. So whatever is going to be inside the root is always going to be a positive value, and taking the third root of a positive value will never get 0. So we're not dividing by 0, so there's no issues here. So this function here is in fact continuous. Good, so we have continuity, so we could apply FTC part 1. So now we could go ahead and take the derivative. Notice that here at this stage, we haven't taken the derivative yet. This is still the original function g of x. We just expanded it. We split it up into 2 integrals so that they're of the correct form. Now we're ready to take the derivative. So g prime of x is equal to, so we're taking the derivative of the first function. Again, we just substitute the upper bound into, replace the t with the upper bound. So we get negative 1 over the cubed root of 2 plus, instead of t to the 4, it's going to be tan to the 4. But don't stop there. Remember, we have to apply chain rule, multiplied by, so here we essentially took the derivative, canceling out the integration sign. And now we have to take the derivative of the tan. So the derivative of tan is secant squared. Okay, so this piece here is done. Plus, let's do this piece over here. So again, the function's continuous. We could we could derive by removing the integral sign, leaving us with 1 over cubed root of 2 plus x squared to the 4. Right, so we're substituting the x squared with our t. Multiplied by the derivative of x squared, giving us times 2x. Okay, and this is our final answer. Okay, so we could simplify this a bit more, writing negative secant squared of x over the cubed root of 2 plus tan 4 of x plus 2x over the square root, not the square root, the cube root of 2 plus x to the x squared to the 4 is x to the 8. Okay, and this is the derivative. This is g prime of x, and we're done. Okay, so in this example over here, example 4, it says to use FTC power 1 to determine whether the function is increasing or decreasing at the specified value. So they give us the function g of x is equal to the integral from negative 5 to x to the 4 of e to the sine of pi t dt. And they want to know, is it increasing or decreasing when x is equal to 1? How do we do that? How do we determine whether the function is increasing or decreasing? Well, we're using FTC power 1 to find the derivative, and we know that if the derivative is positive, the function is increasing, and if the derivative is negative, the function is decreasing at that given value. So let's go ahead, and the game plan is to apply FTC part 1, find the derivative of g, and then substitute the given value, in this case 1, into the derivative and see if that value is positive or negative, and then we could determine whether the original function is increasing or decreasing. Let's go ahead and do that. So we begin with FTC part 1. Can we apply FTC part 1? Yes, our function's on the top. We have a constant. We don't care that it's negative 5. We have a constant on the bottom. And this function here is in fact continuous because you have on the top, you have a sine function, which is continuous. E is continuous because it's an exponential function, and the composition of continuous functions is once again continuous. So continuity is satisfied. We have continuity. Good. So now we have to take the derivative of g of x. Let's do that. So the derivative negates the integral symbol, so that's out. And now we're going to substitute the x to the 4 with the t, giving us e to the exponent sine pi x to the 4 multiplied by, so I substituted the x to the 4 in the t, and then I multiplied by the derivative of x to the 4, which is 4x cubed. Okay, so we found our derivative. Next, we're going to substitute 1, replace the x with 1 to see if this answer here is going to be positive or negative. So what we get is e to the sine of pi times 1 to the 4 times 4 times 1 cubed. Okay. This whole thing is exponential. We know exponentials are always positive. So this is going to be a positive value, and 4 times 1 is positive, so this we expect it to be positive. But let's go ahead and write out the details. 1 to the 4 is 1, so we have on the top sine of pi. Sine of pi is 0, so here what we really have is e to the 0 times 4 times 1 cubed is just 4 times 1 times 4. And any number to the 0 is 1, giving us an answer of 4, which is positive. So what could we conclude? Since g prime of 1 is positive, so it's greater than 0, then the function, the original function, is increasing. At x equals 1. Okay. And we're done. So in this final example over here, example number 5, it says to use FTC power 1 to determine whether the function g of x is increasing or decreasing at the specified value. So g of x in this case is given to be the integral from e to negative x cubed to x to the 5 of the square root of t squared plus 1 dt. And the specified value is at x equals negative 1. So we want to know at negative 1, is this function here increasing or decreasing? Let's go ahead and do that. So pause the video to see if you're able to solve this on your own, and let's go ahead and solve it together now. So the first thing I notice is that the bounds of the integration are functions. They're both functions, so we have to split this up. As we saw in the previous example, let's go ahead and do that. So this splits up into e to the negative x cubed to 0 square root of t squared plus 1 dt. If you went to some other value here instead of 0, that's fine, as long as you continue here with the same value. If you go from 0 to 1, that's wrong. You have to ensure that if you're choosing 0, which you could choose any value you want, it's up to you, 0 is the easiest, this one has to be the same. So I'm going from 0 to 0, and now the upper bound is x to the 5 of square root of t squared plus 1 dt. Okay, so now we're ready to apply FTC power 1, but we have to ensure that the function we're working with is continuous. Is this function here continuous? We have to be careful. We have a square root. We know that we cannot take the square root of a negative. What's in the root, could that be negative? Well, no, because no matter what value you replace t with, you're squaring it, so it's always going to become positive, and you're adding 1 to it. So there's no issues there. So this is continuous for all values of t. So there's no issues here. We have continuity. We're ready to apply FTC power 1. Let's go ahead and do that. So let's take the derivative. So the derivative, oh wait, we cannot take the derivative yet because this part here actually is not of the right form. E to the negative x cubed is on the bottom. This would have been a mistake if we would have applied FTC part 1 at this stage here. So what we have to catch is that the function here has to be on the top, on the upper bound. It cannot be on the lower bound. So what we have to do is switch it. We have to flip it. So in order to flip it, we put a negative in front and then switch the sign, switch the bounds. Switch the signs. This goes to 0. This is e to the negative x cubed. Okay, now we're ready to apply FTC part 1. Had we done that too soon, that would have been incorrect. So the derivative g prime of x is negative. We're going to substitute t with the upper bound, giving us the square root of e to the negative x cubed, all that squared, plus 1, times the derivative of the exponent. So the derivative of what's in the, not in the exponent, what's in the upper bound. So we have e to the negative x cubed. So we know the derivative of e to the x is still e to the x, so we write the same thing. And now we have to take the derivative of what's in the exponent, negative x cubed. So the derivative of negative x cubed, so essentially we're applying chain rule twice. So we get times negative 3x squared. Okay. So we applied chain rule twice. E to the negative x cubed, which keeps us at e to negative x cubed, because the derivative of e to the x is e to the x, and then the derivative of negative x cubed is negative 3x squared by power rule. So that part is done. Now we move on to the second piece. So plus, here we substitute the t with x to the 5, so this one's a lot easier, giving us x to the 10 plus 1 times the derivative of x to the 5 is 5x to the 4. So what we do now is we substitute at x equals negative 1. So let's do that. g prime of x, oh sorry, not of x, g prime of negative 1. So the first thing to notice is that we have two negatives here. So they cancel each other, these two negatives. We're left with 3. We're left with the x squared, which is negative 1 squared. And then we're left with the square root. Oh, sorry. There's this term here. We have e to the negative of negative 1 cubed times the square root of e to the negative of negative 1 cubed, all that squared, plus 1. So this is everything here. Next we have 5x squared, sorry, x to the 4, square root of x to the 10 plus 1. Okay. So, oh, sorry, and the x's are replaced with negative 1. Okay. So if you have a calculator, great, you can just plug this into the calculator to determine whether it's positive or negative. If you're not allowed to use a calculator, let's analyze it. Let's do it that way. So by quickly analyzing, we don't have to actually find the value. We could see that 3 is positive. Negative 1 squared, that's also positive because two negatives make a positive. Negative 1 times negative 1 is positive 1. E to the exponent of any number is positive. Exponentials are always positive. The negative in the exponent wouldn't change the sign of the number. It would just flip the fraction. It would, like if you have e to the negative 2, let's say, that just causes it to be e to the 1 over e to the 2, right? So this is still a positive value. So negative exponents doesn't cause the number to be negative. Be careful for that. So this value here is always positive. So 3 negative 1 squared e to the negative of negative 1 cubed. All this is positive. Inside the root, we have this whole term, which is squared. So since this number in here, whatever it becomes, if it's positive or negative, doesn't matter because you're squaring it. So that turns it positive. And you're adding 1 to a positive value, which is again positive, and you're taking the square root of a positive value. Again, all this is positive. And then this piece over here, so this whole thing here is positive, it's greater than 0. And this whole thing here is also greater than 0 because we have negative 1 to the 4. Since it's an exponent 4, it's an even exponent, this value is going to be positive. 5 is positive. And negative 1 to the 10, again, that's a positive value because the exponent is even. So this value is just positive 1 plus 1, that's 2. This is square root of 2. This whole thing is positive, greater than 0. Since you're adding a positive with a positive, this whole thing is positive. Okay, so without using a calculator, we are able to analyze these values and see if we get a positive or a negative value. In this case here, it's positive. So what could we conclude? We could conclude at negative 1, this function here, g of x, is increasing. Okay, so g of x is increasing at the value x equals negative 1. And that's the final answer. So I hope this helped. I hope you have a better understanding of Fundamental Theorem of Calculus Part 1. So I'll see you in the next one.